Assalamualaikum. The objective of these experiments is that concrete hollow bricks have emerged as highly efficient, sustainable alternative to traditional solid masonry. Their engineered voids reduce the overall volume of concrete required, significantly lowering a building's dead weight to allow for faster construction and more economical foundation designs. And beyond structural efficiency, these internal air cavities act as natural thermal and acoustic barriers, improving indoor climate control and reducing energy consumption. Crucially, this brick supports circular economy principles because of their manufacturing process can easily integrate industrial byproducts like recycled concrete aggregate, also known as RCA. By substituting 30% of natural coarse aggregate with RCA, it drastically reduces of the carbon footprint associated with quarrying materials, offering an excellent framework for balancing engineering utility with aggressive carbon reduction goals. Now, the apparatus for this experiment are as listed, such as coarse aggregate, fine aggregate, water, buckets, cement, a large mixing pan, a mold, trowel, weighing balance, and also a scoop. Now, moving on to the methodology and concrete mix preparation. Now, to prepare the mix, the exact material masses of water is 0.7 kg, ordinary Portland cement 1.2 kg, sand 2.37 kg, and natural gravel 2.94 kg, and RCA 1.26 kg were weighed to maintain a precise 30% replacement ratio. Now, the fabrication followed a dry to wet sequence, where the cement, sand, gravel, and RCA were first thoroughly blended to ensure a homogeneous particle distribution. Once the dry skeleton was completely uniform, the water was gradually added and mixed continuously to activate hydration, yielding a cohesive concrete paste ready for testing.
So for this methodology slide, I will be talking about testing and evaluating. So the compressive strength test. The compressive strength test was concluded to evaluate the mechanical performance and load-bearing capacity of the concrete hollow bricks, incorporating recycled concrete aggregate (RCA) as a partial replacement for natural coarse aggregate. The specimens were tested after the designated water curing period to evaluate early age, strength, development, and structural viability. Before testing is commenced, the hollow brick were removed from the curing tank and my excess surface water was wiped off to achieve a clean surface condition. Each brick specimen was placed centrally between the plates of the universal compression testing machine to ensure an even and uniform distribution of the axial load. The compression load was applied, and the maximum peak load is recorded at the point of failure on the digital controller was documented to calculated. The ultimate compressive strength is achieved, and the hollow brick samples of failure is written and recorded.
Okay, now moving on to methodology evaluation. So after we did the compressive strength test, we know that the RCA substitution affect the structural performance of the fabricated hollow masonry units. By replacing the coarse gravel with the RCA, introduce distinct physical and mechanical variables into the concrete matrix. It is because this RCA containing an adhesive layer of all porous cement mortar. It possesses a higher water absorption rate and potential micro fissure compared to virgin geological aggregates. So next, if the material is mixed thoroughly and compact uniformly within the molds, the water curing paste allow the new cement paste to hydrate effectively around the recycled aggregates particle. This will resulting in strong composite matrix bonding and high load bearing capacities. But however, inconsistency in manual laboratory preparation, such as localized void of uneven density distributions around the internal hollow cavities, can lead to stress concentrations and premature cracking under axial loading. But overall, the evaluation highlight that while an RCA replacement rate is highly viable for producing sustainable structural masonry, rigorous consistency during mixing and fabrication is essential to minimizing strength variations. Okay, so now the summary of the result. So after undergo the compressive strength test, the first concrete block can withstand a total force of 236.55 kN and the compressive strength of 11.83 MPa. So our second compressive test is invalid due to uneven surfaces when testing. So the concrete block can only withstand a minimum force of 6.19 kN and the compressive strength of 0.31 MPa before it fails. So for our third compressive strength test, the maximum force is 173.26 and the compressive strength is 8.66 MPa, which is valid.
So the discussion from our slide is testing hollow concrete bricks were made with 30% recycled concrete aggregate to prove that sustainable mixes can achieve high structural strengths provided they are fabricated correctly. Specimen 1 and 3 reached impressive peak failure loads of 238.55 kilonewtons and 173.26 kilonewtons of proper compaction, allowed in the cement paste to bond tightly with the rough recycled aggregate, creating a uniform load-bearing skeleton. Conversely, specimen 2 failed prematurely at a mere 6.19 kilonewton due to manufacturing flaws rather than a bad mix design. Uneven manual tamping left air pockets along the bricks, the hollow walls, while the porous recycled aggregate sucked moisture away from the cement, creating dry, weak zones that crack instantly under pressure. So replacing natural gravel with demolition waste is a major win for the circular economy, saving nearly 3 kilograms of natural stone per batch. However, because recycled aggregate that drastically reduces a material to tolerance for fabrication errors, real-world production will require strict quality controls, specifically mechanical vibratory compaction and per-saturating the RCA to manage water absorption and ensure structural reliability.
So then, in conclusion, we know that after this 7-day study of replacing 30% of natural coarse gravel or coarse aggregate with RCA, can successfully produce structurally sound hollow bricks specimen. 1 and 3 prove this by reaching impressive peak loads of 236.55 kilonewton and 173.26 kilonewton. validating that eco-friendly machineries can cut emissions and landfall waste without sacrificing strength. However, specimen number 2 have a sudden failure at just 6.19 kilonewton, serve as critical reminder that RCA concrete is highly sensitive to manual preparation mistake and localized water loss. Then to eliminate this structural inconsistency future production, I think we should upgrade from manual tempting to mechanical vibration to eliminate air pockets and swap flexible cardboard inserts for rigid steel or plastic molds. Additionally, pre-structuring the RCA will prevent it from stealing vital mixing water from the cement, while extending the curing process to 28 days will allow for a proper assessment of the bricks' ultimate long-term durability. So the longer the curing process, the longer the bricks.
Now, one of the advantages of using RCA is that it drives a circular economy and conserves resources. Now, RCA construction and demolition waste, which usually accounts for a massive chunk of landfill volume, into a valuable resource. By substituting gravel with recycled concrete, you directly prevent the depletion of natural quarries and minimize the carbon footprint associated with mining raw stone.
So for the advantage, it is stronger mechanical interlocking, as you can see in the image above, right there. Crushed RCA particles have highly irregular, angular shapes and a rough surface texture covered in old dirt mortar. So this jagged profile gives it a physical edge over smooth, rounded natural river gravel, allowing the fresh cement paste to mechanically grip and bond to the aggregate much more tightly.
Okay, now moving on to our next advantages. It is significant logistic and economical savings. So sourcing aggregates from local demolition sites or recycling plants drastically cuts down on material transportation distance and fuel costs compared to hauling stone from distant quarries. And additionally, reusing concrete on site or sourcing it nearby helps project avoid expensive landfill tipping and disposal fees. So the project will cost more money